All right, page 486. We're going to get to your homework in just a moment, but let's review some things from yesterday. Described finding the number of possibilities that exist in an uncertain situation if values or items could be repeated or reused. What do we call this method of finding possibilities in which values can be repeated? Counting. It's like, counting really? Yeah, but counting is the name for finding total possibilities in an uncertain situation where values could be repeated. For instance, Kendall picks blue as her favorite color. That doesn't mean that Genesis can't also say blue is her favorite color. Okay? Values can be repeated, simply counting. And basically the essence of counting is to do what, Audrey? Class? Multiply. That's it, just multiply. So if there's, you had to pick one of 6 favorite colors as your favorite color. If Kendall's picking, and then Genesis is picking, how many different combinations of favorite colors can we make? 36. Kendall could pick one of 6 for her favorite color. Genesis could pick one of 6 for her favorite color. We just multiply the 6 times the 6. Right, if... oh, goodness. Any of you ladies have lots and lots of shoes? You got like ladies, I said. Michael has lots of shoes. See, when I was growing up, like I had like, brown shoes, black shoes, athletic shoes. I did have racing spikes for race days, flip-flops. And then there were the old shoes that used to be my running shoes. They were my work shoes now because they were in terrible condition, so I didn't care if they got messed up. Okay, so I guess that's 6 pairs of shoes, 2 of which kind of you can't count as shoes, but anyway. And so I just kind of assumed that's just how guys work. Girls have like the red shoes, the blue shoes, the black shoes with heels, the black shoes that are flat, and all that kind of stuff. And then guys, just have just enough shoes to get by. And I get to college, and I'm doing okay at college, whatever. I get to my senior year, one of my roommates, freshman coming in, he moves into the room while I'm out, and I come in and I see on the top bunk, which was supposed to be empty, like 24 pairs of shoes. I'm like, what in the world? And then he buys more shoes. And it's like every few days there's another pair of shoes that he's ordered. I'm like, what? This is not normal. So anyway, Michael. How many pairs of shoes you got, Michael? Just rough estimate.
50.
We'll go 50?
15.
15, okay. All right, 15, still a lot, but whatever. He's athletic, so there's the cleats, maybe a few pairs of cleats, indoor cleats, outdoor cleats, lots of pairs of cleats. Okay, so athletes will have more shoes. It's true. And then let's just go soccer here. So you got four sets of soccer cleats and pairs of soccer socks for competition and training. Only 2 pairs of socks, really. All right, both white.
White and red.
White and red. Okay, I was about to say black's usually for officials, but white and red. Okay, so 2 pairs of soccer socks. Soccer shorts, probably several pairs.
2 or 3.
Only a couple. Okay, so more so on the shoes, and then soccer type shirts. I guess uniform shirts. Probably only a few, but a lot of uniform shirts.
It's because I always wear athletic shirts.
Okay, so anyway, so let's just say 8. Let's say 8. Okay, so if we were trying to put together his outfit, how many different outfits could we come up with? Well, we would multiply, class, the 15 pairs of shoes times the 2 pairs of socks times 2 pairs of shorts times the 8. We're not actually going to do it because we don't care that much. But that's multiplying. That's counting, right? Counting is where you just multiply values together if they could be repeated, right? The fact that he wears his indoor soccer shoes with red socks doesn't mean he couldn't also wear indoor soccer shoes with white socks sometime, right? That's where we have just basic counting, just basic multiplication. Then we got into another situation where values couldn't be repeated. If you were to put the indoor shoes with the red socks, well, the indoor shoes would not be reused. Actually, that's a different scenario. Let's go with Kendall and Genesis again, with the 6 main colors of the rainbow. And Kendall says, oh, I like blue. And Genesis is like, man, I was going to pick blue. Now I got to pick something else. Well, now, instead of having 6 options to choose from, if for some stupid reason she's not allowed to pick blue, how many options does she have now, class? Only 5. That's not basic counting. When a value could not be reused, we refer to that as a permutation. And specifically, if the order matters. Kendall picking blue and Genesis picking purple? Yes? Okay, Kendall picking blue. I don't know about Kendall, but I know Genesis likes purple. So Kendall picking blue, Genesis picking purple is different from Kendall picking purple and Genesis picking blue. but we still have 30 possibilities, 6 and 5, right? That's a permutation. Part of the permutation, though, use this little this symbol, this exclamation point. What is this? How do we read that exclamation point, Maddie? It means a particular word. Factorial, you read well. Factorial, and what does it actually mean? For instance, if we had 8 factorial, what does that mean?
8 times all the numbers below.
Yeah, so for instance.
8 times 7 times 6 times 5 times 4 times 3 times 2 times 1.
See, there we go. And I didn't pick 10 factorial. All right, so yeah, all those numbers are multiplied together. Well, we use this notation for permutations as well, or for the permutation formula, which should be on your formula page. What's the notation for a permutation, Brandon?
So then P sub.
There we go, a subnotated N and R on either sides of a P. I just say NPR because at that point I'm too lazy for the other. But the NPR shows a permutation where the N represents the total number of options available. For instance, in the case of Kendall and Genesis, 6 total colors to choose from, which seems vague. How many of your favorite color is not one of the big 6? Your favorite color is like a specific, like, I like aquamarine or fuchsia or something like that. Anyone have a favorite color that's outside the...
What are the big 6?
Red, orange, yellow, green, blue, purple?
Okay.
Yeah. Yours would be...
Well, I have specifics of...
So specifically...
mint.
Mint. Okay, so a very specific shade of green, right? So, but if you had to pick one of the main 6, okay? So 6 was the number, and then R would be how many people are choosing. In this case, in Kendall and Genesis class, the R would be 2. What's the formula for a permutation that we were using last night as we did the homework? Michael?
N factorial over N minus R factorial.
Good. N factorial over N minus R factorial. And again, this is what we'd use when values cannot be repeated and the order makes a difference. Page 46, homework was numbers 2 through 14 to even. Number 2, an electronic lock to a particular safe uses 4 letters followed by 4 numbers. Assuming that letters and numbers can be repeated, so you could have A, 1, 1, 1, 1, however many, 4 of them. How many different passwords are possible? What was your answer here? Genesis, a huge number.
4,160.
Okay, yeah, way bigger than that. So there's how many different numbers or values in the password?
4.
Oh, that's okay, maybe that's but there's 8. So there's 8. And this is going to be a letter, number. Okay, so that's the first thing. There's going to be 8 of them. Well, for letters, how many different possibilities are there? 26. So for this letter, there's, well, if they couldn't be repeated, you'd be right, but they can be. So 26, and then again another 26, and then another 26, and there's 10 different numbers, 0 through 9, and then 10 more, 10 more, 10 more. And we should have actually multiplied all of those together. Like I say, it's an enormous value. Kendall?
4,569,760,000.
Yeah, 4,569,760,000 different passwords would be possible there. How many had that enormous number? All right, does it make sense now, Genesis? All right, looking at number 4, within a particular area code, each phone number has 7 numbers, 0 through 9. Assuming the numbers can be repeated and no 7-digit numbers are excluded, how many different phone numbers can be created? What did you have for this answer, Audrey?
10 million.
10 million. We've got a particular area code. For instance, here in Columbus, Georgia, it's 706. And then there's 3 digits dash 4 digits, right? So 7 total digits. Well, it's literally 10 possibilities for every one of them. And so, sure enough, there's your 10 million different phone numbers you could make in that one area code. How many had 10 million for number 4? Questions on number 4. And number 6, for a particular internet password, a customer is required to have 5 letters, A to Z, and 2 numbers in that order. If the letters and numbers can be repeated, how many possible passwords are there? And another big number here, Brandon?
1,188,137,600.
Good. 1,188,137,600. How many had that for number 6? All right, in Genesis, that one's going to be very similar, right, to number 2. So take a moment to re-enter that. Did you get that 1,188,000,000 number? All right. Questions on those? Again, what's the key phrase that shows up in all three of those questions, class? Can be repeated. When you see can be repeated, it's just a straight up multiplication, no permutation needed. As soon as something can't be repeated, now we're going to the permutation. But they didn't give us cool problems. We had boring problems for permutations. So for numbers 8 through 14, the even, they gave us 13 P6, which means there's 13 possible things to choose from. 6 of those items are going to be chosen in whatever order, and each order would be different. What is a permutation of 13 items taken 6 at a time, Abby? Number 8.
1,235,520.
Good. 1,235,520. How many had that for number 8? Good. We're going to do 13 factorial over 7 factorial. And your calculator can do that. Or you could do the 13 factorial, 13, 12, 11, 10, 9, 8, 7 factorial, and then cancel the 7 factorials. But I think it's quicker to do it on the calculator. For number 10, 14 items taken 6 at a time. Genesis? Good, 2,162,160. How many had that for 10? Number 12, 19 items taken 7 at a time. Maddie, how many possible arrangements? Good, 253,955,520. And a much smaller, easier one. Number 14, 8 items taken 5 at a time, Michael.
6,720.
6,720. How many had that for number 14? All right, questions on basic counting, just multiply stuff, and permutations, where we have a formula to follow. All right, that permutation, remember, means the order's different. If Kendall picks blue and Genesis picks purple, that's different, Abby, than Kendall picking purple and Genesis picking blue. But what if we're like, hey, these two girls are going to pick their favorite colors. What are the odds that blue and purple are the colors taken? Well, if you don't really care who picks what, it's just that blue and purple, hey, the bottom of the rainbow just got taken, whatever, right? If the order doesn't really matter, but you still can't reuse something, that's no longer a permutation, but next section of your notes, it is a combination. A combination. A combination specifically refers to the number of possibilities. A combination is the number of possibilities in which values may be arranged. The number of possibilities in which values, can't be repeated. That's like a permutation. The number of possibilities in which values can't be repeated. That's just like a permutation so far, but order does not matter. That's the difference. Permutation, the order makes a difference. Combination, you don't care what order, it's just what was taken. Okay, number of possibilities in which values can't be repeated, but order does not matter. For instance, let's actually get to the red, orange, yellow, green, blue, purple. How many have ever played croquet? It's an outdoor lawn game. Okay, you have. There's a mallet about so long. Hit a ball. It's kind of like golf, but you hit it through little white, what are called wickets, but you hit it through and you try to hit a stake and stuff like that. Anyway, there's 6 croquet balls. All right. If Kendall picks the purple ball, Genesis can't have the purple ball because they're all 6 of the balls that are different colors. Okay, so once something's taken, it's taken. Let's suppose there were just 2 people. Maybe it is Kendall and Genesis are going to play croquet. There's 6 balls, red, orange, yellow, green, blue, purple, and violet, whatever. And 2 people are going to play the game. Well, obviously it could be that Kendall picks red and maybe Genesis picks orange. Maybe Kendall picks orange and Genesis picks yellow. Maybe Kendall picks red, Genesis picks yellow. Maybe Kendall picks red and Genesis picks green. You get the idea. We could pick a lot of these. However, orange and red would not be another possibility. Because all we're looking at is which 2 balls have been taken. If we don't care who has what, we're just interested in which 2 balls were selected, then orange and red would not be a different option from red and orange. Does that make sense? That's what we mean by this. Well, the formula we're going to have here, write this in your write it in your notes, and then also we'll put on the formula page. For n objects chosen r at a time for a combination where order doesn't matter, we're still going to have that n factorial. We're still going to have the n factorial But in the denominator, we're going to have both r factorial and n minus r factorial. We're going to have n factorial divided by both r factorial and n minus r factorial. So we see the little addition right here. Here's the idea. The two balls, orange and red, were chosen. In a permutation, red, orange, and orange, red are two different possibilities, right? But in a combination, we divide away that two possibilities, which would be your r in this case. So if you want to add this to your formula page, this is our formula for a combination. Anytime the order doesn't matter. So a combination of n items taken r at a time is n factorial over r factorial n minus r factorial. All right, in this specific case, 6 croquet balls chosen 2 at a time. How many different possible ways could these girls select the two colors they end up using? Well, we're going to start just like we would in the permutation with the 6 factorial. But we're not only going to put the 4 factorial like we would for a permutation, but if we don't care who has which ball, the fact that there's 2 different ways that specifically those 2 balls could be arranged, we'll divide that 2 factorial, which is 2, away also. One way you could show it then would be 6 times 4 times 3 times 2 times 1 over 2 times 1 times 4 times 3 times 2 times 1. Not necessarily a huge fan of doing this, but you see that the 4, 3, 2, 1s could cancel. The 2 cancels with the 6 to give me 3, and with how many possibilities? 15. Possible ways that any 2 balls, regardless of who has which, could be taken. Again, like a permutation, but you also divide out the r factorial. That's the only difference in the formulas. Make sense? Because this basically reduces the number of possibilities. Again, if blue and purple is different from purple and blue, that's going to make more possibilities, right? If we're dividing that out, we want fewer possibilities. Let's suppose, for instance, we had a classroom with 15 students in it. And Mr. Keys came to the classroom with, hey, I need 3 people to help me for something. Does it really matter which order people get chosen? Not really. It's just, I just need 3 people, right? So if it's just, I just need 3 people to help, since we don't care about the order, we would say we have a combination of 15 students, 3 of whom have been chosen. How many different groups of 3 could we take? And again, that means that if Brandon, Audrey, and Abby are taken, that is not any different than Abby, Audrey, and Brandon. Same 3 people. Who cares what order they were taken out of the room? All right, so in the numerator class, we would put 15 factorial. And in the denominator, we would put both the 3 factorial and also the 12 factorial. Again, if we wanted to work it out without the calculator, 15, 14, 13, 12 factorial, all over 3 factorial, 12 factorial. You see the 12 factorials cancel. What is 3 factorial? 3, 2, 1, right? 3, 2, 1. The 3 could cancel with the 15, and the 2 could cancel with the 14, 7. And you could multiply 5 times 7 times 13, and suddenly we need the calculator anyway, because we're too lazy. And so how many different groups of 3 kids could be taken from a room with 15 students in it?
455.
How many? 455. All right. Remember the other day I gave the example of kids in PE, how many kids on a team? Does it really matter at the end of the day who was first pick, second pick, third pick? Not really. I mean, if there's public humiliation on the line, sure. But especially since in my PE class, right, we do it secret, they take the captains aside, they pick their teams. All that really matters is which kids end up on this team versus which kids end up on this team. Let's suppose we've got, let's see, in my PE class right now, we've got 18 kids, which means 9 students would end up on a particular team. How many different ways could a team be chosen? How many different ways could 9 kids out of 18 wind up on a team? Well, in the numerator class we'll have 18 factorial. In the bottom we'll have 9 factorial and another 9 factorial. And by the way, is that the same thing as 18 factorial? No. Quickest, easiest way to do this, I think, is just to plug it into the calculator. So here's what I would suggest. I would suggest plugging in 18 factorial, that's that second function of the 3, divided by, there's your fraction bar, and then you're going to want to put parentheses. around the denominator, because the fraction bar also groups. A division sign doesn't, so we're going to put the parentheses, divided by parentheses. Do we know where the parenthesis keys are, by the way? Okay, right here above the 8 is an open parenthesis. 9 factorial times 9 factorial, close the parenthesis, which is above the 9 button, and hit equals. And let's see what we've got here. How many different PE teams could be constructed with 9 people out of 18? Kendall? 48,620 different teams could be formed with 9 people in a class of 18. So the odds of a particular group of 9 is actually pretty, how many have that same answer? 48,620. I mentioned before with the state championship, right? You got 16 runners, the top 3 win medallions. It does matter the order, first, second, and third, because that's winning a medallion. But let's suppose we're at the regional level, and your goal is to advance to state. Now, you'd love to win first, but all you care about is getting to state. Getting to the state competition, you got to be one of the top 4. So if there's 16 runners in the regional race, the top 4 in any order, it doesn't matter. That's the key. Order does not matter. The top 4 get to go to state. How many different groups of runners could go to the state could go to the state race? 16 runners. The top 4 will go to the state race. And we take 16 factorial. Don't forget the parentheses. Divided by 4 factorial times the 12 factorial. Now, obviously, there's other probabilities built in there, like, well, these runners are just faster than everybody else, so they're probably going to go. Okay, so this is a true probability, but if you had to pick without any knowledge at all, what are the odds of you picking the right 4 people? Audrey?
1,820.
Yeah, there's 1,820 different groups of runners that could go. You're unlikely to pick those 4 exactly. How many had that answer? All right, feel like we understand how to use this? All right, look at page 45. Flip back a page real quick. Page 45. Now look at actually look all the way back at page 44 for just a moment. Page 44, you see the example problem we looked at the other day, evaluating 20p8, permutation of 20 take 8? Look at how many possibilities there are. 5,079 million, so forth, right? Look now across the page at page 485, example 10.6d. They use the same 2 numbers. 20 objects, 20 things, whatever, taken 8 at a time, but now we don't care about the order. Notice how much smaller the number of possibilities is. If we don't really care about the order specifically, now there's only 125,970 possibilities. Do you see the difference between the combination and the permutation? You're always going to get more possibilities out of a permutation if you start obsessing over the order that things fall into. And sometimes it's fair, right? Like if we had a class election and, say you're all in the same class, even though we've got 3 classes represented here. If we were going to take a class election and we're going to vote for a president, vice president, and treasurer. Well, getting voted president is way different than getting voted treasurer, right? So would we use a permutation or a combination? Permutation. But if I just said there's 7 of you in here, hey, we need 3 people to help. Does it matter what order you're taking? No. So that would be a combination. We see the difference of when to use what. That's something we're going to work on a lot more in the next lesson. For now, though, turn to page 486. Page 486. And let's take a look at number 25. Number 25. Solving a combination of 13, choose 5. Combination of 13, choose 5. What is my formula for the combination? Michael?
NCR equals n factorial over r factorial times the quantity of n minus r factorial.
There we go, perfect. And so for this in the numerator, we're going to put
13 factorial.
And in the denominator, we're going to put 2 different factorials.
5 factorial times 7 factorial.
8 factorial. All right. And again, if we wanted to do it the long, slow, painful way, maybe didn't have a calculator, yes, it's doable. You could 13 times 12 times 11 times 10 times 9 times 8. It pains me and my lazy self to do it. But I mean, heaven forbid, worst case scenario, you lost your calculator, couldn't find it. showed up for class. It's going to take you a lot longer to do, but you could still work it, I suppose. 5, 4, 3, 2. I'm too lazy to write 1. A factorial. Remember, you'll take whichever is the bigger factorial, cancel it with where you left off there. And then notice 5 and 2 could cancel with a 10. 4 and 3 could cancel with a 12. So all I've really got is 13, 11, and 9. Of course, we know 9 and 11. 99, and multiply that by 13. Of course, you're going to use your calculators anyway for that. But 99 times 13 would be 1287. Number 27. 15C11 means in the numerator I'm going to put Genesis. I'm not going to put Genesis in the numerator. Genesis, what will I put in the numerator? 15 factorial, good. And in the denominator? Factorial. And 4 factorial. Good. If it were a permutation, it would only be the 4 factorial. Because it's a combination, the 11 factorial is in there as well. And not a whole lot of possibilities here compared to some of the other numbers that are in the millions and billions at least. If there were 15 objects and you had to pick 11 of them, how many different groups of 11 could you make? Good, 1,365. How many have the same thing here? Feel pretty good about combinations? All right, do 29 and 31. 29 and 31. Just 29 and 31. Good, Audrey. Michael, Abby. Here's a question for you before we take a look at this. What if I wanted to see how many different ways the 7 of you could finish a problem? Now, most of the time, who's the first one done? A lot of times Abby, a lot of times Michael, right? Usually kind of up there, Brandon and Audrey. But if we were to say how many orders could people finish in, would that be a permutation or a combination? It would be a permutation, wouldn't it? Because the order is what we're actually looking for, right? But it would be a permutation of how many people taken how many at a time? 7. This would be a permutation of all 7. Notice how this would work out. 7 factorial over n minus r factorial would be 0 factorial. I meant to review this earlier. What is 0 factorial? 1. So in other words, it's just 7 factorial. In other words, if every item in a group is chosen, it's just that number factorial. So if we wanted to see how many different ways you all could finish something, Abby, it would be
5,040.
There's 5,040 different ways you guys could finish. That doesn't mean that will always be that many ways, but that's how many could be done. Anyway, thought I'd review that real quick with you. So we were on number 29. And what did you get for a combination of 10 objects chosen with 5 of them being chosen? Genesis? 252 is correct. Number 31, if there are 12 objects, 9 of which are going to be chosen, how many different ways could that happen, Maddie? 220 different ways. How many of both of those correct? A little bit smaller numbers that time. All right. Do the 26 to 32 even. 26 to 32, the even then. There's trauma happening all around us. Happily oblivious. Or mostly. It's tough to listen to the sounds. That's the worst part, isn't it, Brandon? His brother wasn't feeling well this morning, in case you're wondering. He got it right away. All right, number 26 on that happy note. 14 objects chosen, 9 of them at a time. We don't care about the order. How many different ways could these be arranged, Abby?
2002.
2002, that was a good year. Actually, it was a lousy year. I was in junior high. Horrible year. Number 28. Were any of you born in 2002? Babies. All right, Genesis. No, even she wasn't born in 2. Yeah. All right. No, duh. That would make you 20 at this point. None of you. Okay. Stupid question. I didn't do the math. I'm old. Anyway, number 28. 9 objects taken 6 at a time. What's our combination there, Audrey? 84. For number 30, 20 items taken 6 at a time, Michael.
38,760.
38,760. And then 25 objects, 11 chosen in a group. How many different groups could be formed, Kendall?
4,457,400.
Good. 4,457,400. How many had all 4 of those correct? All right, good to go with that. Maddie's checking on one of them, I think. Which one?
Number 26.
Number 26. So in the top you had,
14 factorial.
and in the bottom you had 2 things.
9 factorial. And then 5 factorial.
And that's right. Take a moment and enter the calculator. The number again was 2002. Just a minute to confirm she's got it. Got it now. Okay. All right, so maybe probably a calculator entry here. Again, as I've mentioned before, as long as it's written, if I see 14 factorial over 9 factorial, 5 factorial, and you have a totally wrong answer, if I see this, you're going to get most of the credit. Because I know, okay, you're human, finger pressed wrong button, or you forget to close a parenthesis, or something weird like that happens, whatever, right? But if I can see this on the paper, I know you understand it, I can give you most of the credit. So gives me opportunity to mention that to you. So real quick refresher here then. If you can reuse a selection, for instance, we have our classes trying to decide who's going to do what here, and we're like, we need 4 people to take care of some different things. We need somebody to draw pictures for field day on posters, and we need somebody else to sell tickets for field day, and we need somebody else to plan all the games for field day, and I need a 4th job for field day. We need somebody else to print flyers for field day. And so the class gets together, always the juniors get together, and you all decide, I think Michael ought to print the flyers, and Michael ought to plan the activities, and Michael ought to do all the artwork, and Michael ought to sell the tickets.
You should have done Audrey.
All right, now you can technically do all 4 of those things at the same time, because they don't actually coexist. So in that case, since selections could be reused, right, if you need 4 jobs to be done, and there's 3 juniors, the first job class, there's, well, how many juniors are there? For the first job, there's 3 people who could do it. For the second job, there's 3 people who could do it, because a person could do both. For the next job, there's still 3 people who could do it. For the last job, there's still 3 people who could do it. So technically, if a person could do all the jobs, then we would here just use basic counting. That's just multiplication. But if you couldn't reuse or repeat, for instance, if the 3 of you decided to select a hierarchy of president, vice president, and treasurer, well, order matters, right? The president is over the vice president, gets bossy. Michael's like, right here. Yep. And so, but technically, odd as this may seem to Michael, how many people could be president? 3. But you can't do both president and vice president. Jokes about people who can't do either aside. You can't do both president and vice president. So how many people could be selected for vice president? 2. And this wasn't a reference to our juniors, by the way. And then whoever didn't get president or vice president by default gets to be treasurer. So here, this is essentially, remember, that permutation. A permutation of 3 people, and we need 3 offices filled. Again, it ends up being a basic factorial. But if we just need, we can't reuse or repeat people. For instance, I need 3 helpers, Michael and Michael and Michael. Come help me real quick. I didn't get 3 helpers. If I really need 3 helpers, but the order that I pick them in doesn't really matter, then class we would use the combination. And a combination of 3, pick 3 is stupid sounding, but because it'd be the same as the permutation. Actually, it wouldn't be. For the permutation, remember, the top is going to be class the 3 factorial over 0 factorial for a permutation. For a combination, it's still going to be in the top 3 factorial, but in the bottom you're going to put the r and the difference. So if it was just the 3 juniors, and I walk in a room, I need 3 people to help me. Who am I going to pick? How many different groups could I pick? 1. There's only 1 group of 3 that exists, right? So in that case, questions on the differences here. Because when we get to word problems next week, you're going to have to figure out which one to use. And that's where the real trick comes in. The good news is, I can free you from a lot of the other math work. Because if you have a scientific calculator, I've been cheating, I'll admit it. I haven't been typing in what you've had to type in, because I'm a lazy slob. There's a shortcut on your calculator. If you look above the 9 key, not the button above the 9 key, but the second function of the 9 key on the TI-30XA, do you see that little NPR notation? So look at number 15. It wants a permutation of 15 choose 9. Do you see it? Literally what I've been doing is I've done 15, second function 9, 9 equals. And it does the whole process for me. And that would be 1,816,214,400. Did you two find your permutation function?
No, I just had a really easy way still.
You still had an easy way.
I can do it all in a fraction.
That's true. You could set up a fraction. Does yours do likewise if you have a similar calculator? All right. So you don't necessarily need an NPR button. But I mean, we literally type, button, type, equals, and we're done. Look at number 17. Use the NPR code, the second function of the 9 key, to do number 17, 17P5. And what do we get? Abby?
742,560.
How many got 742,560? Showing it for the camera here. The next one was number 19, so it's 30P6. So go to the calculator here for the camera's sake, 30, type that in. Second function, the 9 where it says NPR above it, and then you hit the 6. When you hit equals, it gives you the permutation of 30 choose 6. And what do we end up with here? Brandon?
427,518,000.
And all the zeros after that. Yeah, 427,518,000. How many have the same answer? All right, so it's a little quicker, right? Now, the factorial button was still great, right? That really helped speed it up. This speeds it up even more. Number 21. 14P5 equals. That's a cool number. What do you get here, Genesis?
240,000.
Yeah, 240,240. How many have that? All right, and then 23. This is going to be a big one, 13P10. Yep, it's a dilly.
24?
Oh, number 20. 23 is what I said. That one's not such a dilly. 9P5. Yeah, not nearly as bad. What do we get for number 23 here? Kendall?
151. 15,120.
Don't you wish your calculator did commas? 15,120 is correct. Are we good on the permutation? Now look above the 8 if you haven't already noticed. There's the NCR. We do combinations the same way, which is a really nice one because that's one where otherwise we'd have to do 2 denominators, remember? Parentheses, factorial, all of that we're done. We just type in the 2 numbers. So on number 33, up 21C7, it's going to be 21, second function 8, which is the NCR, 7 equals. And we should get what for number 33? Audrey? 116,280. We get that value. 116,280. All right, number 35, 10C7. Oh, really small. What do we get here, Michael?
120.
120. About number 37, 12C3. And what do we get here, Maddie? All right, you found it on yours. All right. Ah, you did find it. Excellent. All right, good, good, good. I was about to say, you weren't putting in all the keystrokes I thought you'd be putting in, so I wonder if you found it. You did. Excellent. And you said we get what now? 220 for number 37. So number 39, 18C6. By the way, of course, if you're watching on YouTube, you're like, I can't find it on my calculator because I didn't get the TI-30XA like you told me to. I'll show you how to use it. Just video chat later. Number 39, Brandon? 18C6?
18,564.
18,564. Then number 41, 19C12. And then come back around to Abby.
50,388.
50,388. We feel good with the button on the calculator. So, the only thing we have to worry about on the word problems, keep coming back to that, is which one, right? Because if it is a permutation, easy, right? We don't even have to remember the formula to do it. Now, on a short answer question, what's the formula for a permutation? You need to be able to write NPR equals n factorial over n minus r factorial. But you ain't got to do it because you're lazy. You have to know it, but you don't got to do it because your calculator is going to do it for you. If it's a combination, again, you need to know NCR is n factorial over r factorial n minus r factorial, but you don't actually have to do it anymore. We've got a shortcut, as long as you have your scientific calculator. If you have a normal boring calculator, hell then help you. All right, let's go and review some more counting scenarios because I feel like that's still giving us a little bit of trouble here. Like ice cream? Okay, let's think ice cream here. So jot down some things as I give them to you. When you go get ice cream, most ice cream restaurants, I guess if you want to call them that, like Brewster's or let's say Baskin Robbins, for instance, there's usually about 4 ways you could get ice cream. You could get the bowl, which is boring, the cake cone, which is sad, the sugar cone, which is all right, and then the waffle cone, which is where it's at. So there's 4 ways to eat the ice cream. Got that? And then let's suppose it's Baskin Robbins and there's 32 flavors of ice cream. And let's suppose you could either get single, double, or triple scoop. How many different ways could a customer step up to the window and order ice cream? Again, they could get either bowl, sugar cone, cake cone, or waffle cone. They could get 32 different flavors of ice cream at Baskin Robbins, and you could either single, double, or triple scoop. How many different ways could a customer step to the window and order ice cream? And what you got here, Brandon? 384. How many have the same answer? 384. What are we going to multiply, class?
32 times 4 times 3.
Oops. Yeah, 32 times 4 times 3. Or if you go in the order I gave them to you, 4 times 32 times 3, right? Again, just because one customer picked something doesn't mean another customer couldn't pick it. And there, really, it's not reusing anything. All right, Georgia license plates. Georgia license plates. Letter, letter, letter. Number, 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 number. And if they can be reused, how many different license plates? It's letter, letter, letter. I'm just going to write as an example. A, B, C, 1, 2, 3, 4. How many different Georgia license plates, if you could have 2 of the same letter, 3 of the same letter, 2 or 3, 4 of the same number, how many different possibilities exist? How many different license plates can Georgia make? And of course we have different designs on the license plates too. You really want to get it right. Michael, how many different license plates?
I have no idea.
All right, Kendall?
17,576,000.
I have an extra 0 in there. Let's see. 26, 26, 26, 10, 10, 10, 10. So I think you might have left off a 10. So should have had, how does your the end of your original answer?
175 million. 700.
760,000 is correct. 175,760,000. How many got that now? Does it make sense? If you're going to have letter, 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 number, 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 and you can reuse, well, there's 26 things you could put in each letter spot, 10 things you could put in each number spot, and they all just get multiplied. Let's suppose, I feel like this one's already been done. We're making a phone number. First area code 706. How many different phone numbers if values can be repeated? How many different phone numbers if values can be repeated? 706, blank, 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 dash, blank, 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 blank. How many different phone numbers could have this area code? I realized as we were going over the homework, oh, well, it doesn't hurt to do it again, I guess. Michael?
10 million.
10 million. Why? Because we're going to multiply.
10 times 10 times 10 times 10 times 10 times 10 times 10.
What's the quick way to do that, class?
10 to the 7.
10 to the 7th, right? You could do that, by the way. Remember the y to the x button above your division key? 10, y to the x 7 would give you the same answer. Now, technically, that's not true. For instance, you will never have the first 3 digits be 911. You'll never have by the way, the first 3 digits be 555 either. And I believe you can never have a 0 for that first digit as well. So if I remember correctly, there are some restrictions on it, but hypothetically. Let's see, some of you have been here for years. You've been here for 11, 12, 13 years. Maddie, you've been here a long time as well. I think you two would be about the only people who remember this. Remember back when the school uniform had more than just blue and gray? You know, you used to have the school uniform had either navy blue, are you listening here? Navy blue, light blue, gray, white, or a weird yellow. There were 5 different colors of uniform shirts. And I believe pants and skirts could be khaki, gray, black, or navy. So how many different ways could you wear a uniform to school back in the old days? Again, you could have light blue, yellow, white, gray, or navy for the shirt, khaki, gray, black, or navy for the pants or skirt. How many different ways could you wear a uniform to school? Maddie? 20. We just multiply the 5 times the 4, and we have the 20 possibilities. Questions on counting again, because I feel like that's the thing that's been giving us the most fits. I feel like permutation, combination were good, and then the counting throws us off. Questions? All right, homework for this evening, for the weekend. Really easy, because you're going to do it all in the calculator. It should take you about 3 minutes tops. Homework is due page 486. Page 486. You're going to do 16 to 24 the even, 16 to 24 the even, and 34 to 42 the even. 34 to 42 the even. It's combinations and permutations on the calculator. Shouldn't take you long at all. The longest part is writing the answers down. It's quicker to do the work than it is to even write the answer down. So should not take long. Have a wonderful weekend, and we're going to get into word problems that apply these principles on Monday. Have a great day.